Okay. Good morning, everybody. Welcome to the, the fourth class of Control Systems 2. So let's start with a few administrative notes, as usual. You have signed up for the hardware exercises. At the moment, the counter is up to 90 and growing. Let's say that we were hoping for at most 50 participants because of the hardware limitations. So twice as much means it was a decent estimate. Typically, every time you make an estimate on something, just multiply it by pi and you get what you actually need. There's always a pi in life somewhere, so it's typically it happens in estimates. So now we have 90 participants, checked 5 minutes ago. The deadline for
91
this,
now. Dr. Tani, 91.
91, fantastic. We should have put the deadline at the beginning, not the end of the class. Anyways, so you have time until the end of the classes to sign up, after which it's done. And we would like to invite you to sign up on the next sheets now. If you signed up to the exercises, we already uploaded a new form that regards the groups. So we will have groups of 5 people. You are free to choose your own groups. So we ask you to just elect or select a group leader. That's just a way to talk to a single person and basically assign a name to each group. Get together, decide who's part of the group, and submit one of these forms for each group. Okay? So if you do not have a group, 5 buddies, or you don't care, you don't want to be assigned with your typical buddies, but you want to experience just a random matching, then just add no members of the group, and we will take care of it. Okay? Yes. So I've been asked about the grading system for these exercises. Many of you, and I'm surprised to some degree, are, I wouldn't say worried, but interested in the competitive part, in the sense that you are afraid that you'll put lots of effort, because lots of effort will be required to do the hardware exercises, and eventually get no bonus because maybe for any reason you don't win the competition or something. Of course, we will not set it up in that way. Okay? We will set it up such that if you complete the exercises, so there's going to be 3 exercises. Each one has a script to follow so that you can play around with the parameters or different controllers or whatever it is in order to see what happens in real life. And the script is even somehow to hide from you all the stuff that is actually going on the robot that is not the topic of this course. Okay? We cannot talk about computer vision. We cannot talk about recursive estimation. We cannot talk about that kind of stuff. So we can't just give you complete access, otherwise you won't understand what is going on. But the script focuses on the control stuff that we did in class. So the competitive part is going to be a bonus on the bonus. Let's put it like this. It's more an opportunity to enjoy stuff while we are working. It's like playing instead of working. The objective of the competition for us is that you spend the time on the platform, that you just don't work on it because you have to satisfy a checkoff or just mark a box, but you do it because you are motivated to just improve it as much as you can. So you can spend time on it, and eventually you'll learn more. Then the competition is just for the laugh and giggles, basically. Okay? Don't worry about the competition. So to give a more concise answer, you're going to get bonus points regardless. If you complete the exercises, you'll get more bonus points if you arrive in the top 50% of the competition, something like this. Okay? Any questions regarding this? Yeah? No? Question? No. Okay, so let's move on to the class. Today, we are going to look at continue developing tools to analyze multi-input, multi-output systems. Just a quick recap of what we've been doing till now. We started the course by focusing on really the important things. What is the objective of a controller? A controller is meant to guarantee stability, performance, and robustness. Then we found, okay, we looked into, okay, but if we want to achieve these objectives, what are the actual constraints? What stands in our way? And we saw that there are two pillars of constraints, the ones that are fundamental, like you have a right-hand plane 0, or you have, I don't know, some delay in the system. Those are things that there is little you can do about. We looked at the waterbed effect that showed us that we can't just arbitrarily shape the sensitivity functions of the system in the way we want, because there are some fundamental conservation laws. We called it the principle of conservation of dirt. Not we called it, but... And then we looked at some practical limitations. At the end of the day, when you design a controller, it's not good if you just have it on paper. It's good if it's actually implemented in a system. Most of the systems nowadays run on computers. They're digital. So we saw that passing through continuous time and discrete time, it's not just a straightforward plug in the number. There are some things that have to be kept into considerations, the approximations that are done in sampling and in doing the digital to analog conversion. We saw that there is a risk during sampling to lose information in the system, but that is covered if the sampling rate is fast enough. And we looked at what does it mean to have a stable discrete system. Then we decided that we have talked enough about CISO systems, and we started moving in an opposite axis, that is in an orthogonal somewhat axis, which is that of now expanding the number of systems that we can apply everything we know to, okay? So we started talking about multi-input, multi-output systems that at the end of the day are most systems that you find in life. So we talked about very basic things of multi-input, multi-outputs. I wouldn't say basics, but I would say fundamental things of multi-input, multi-output systems, such as the fact that they don't have transfer functions, but they have these transfer matrices, which is a striking difference with CISO systems. And that's quite natural if one thinks about it, because there are multiple inputs and multiple outputs, of course. And imagine setting to 0 all inputs apart from 1. Well, that input will have some effect on the different outputs. And of course, the transfer matrix, each element represents the transfer function, as we know it for a CISO system, between that specific input and one or more outputs of the system. We saw that on top of transfer matrices, there is another big peculiarity of MIMO systems, and it's the concept of directionality. There are properties of a MIMO plant change depending on the directions you look at. We even saw that you could actually have poles and zeros at the same frequency in a system without them canceling out if they were at different directions. So today we will look at, we will develop some tools. It's going to be a little bit of a I would say, a class where we will develop tools that will be useful later on. We will look at signals, we will look at ways to compare signals and or systems, or let's say we will try to measure what are the sizes of systems or sizes of a vector or of a signal. So we will talk about norms, which you probably know already, but we will recap in a structured way, building up to the systems norms that we need. Then we will go into singular value decomposition, which is a way to study the directionality of MIMO systems. So today we're going to look at how to study these directions and how to quantify relationships between different quantities involved in a control system. And then we'll talk briefly about stability of MIMO systems, and we will see that it's not very different from what we already know. So just to recall briefly, there are transfer matrices. The equations are pretty much the same, but each element of the transfer matrix of a CISO system can be expressed as, of a MIMO system, can be expressed as a transfer function of a CISO system, and it relates a particular input channel to an output one. It's important to be careful with the dimensions of matrices because typically, matrices do not commute, okay? So if you switch the order of the multiplication, you don't get the same result. That's why when we talked about sensitivity functions in the same way as we did for CISO systems, sensitivity functions are going to be useful to quantify the performances of MIMO systems, and we'll talk about this in the next class. we have to actually be careful where we cut the loop, where we evaluate the sensitivity functions. If we're doing it at the output or at the input, the signals pass through the different blocks, the controller and the plant, in different directions, so you get opposite orders of multiplications, and that change what the result is in general. So we then looked at poles and zeros, and we basically said that poles, as in seesaw systems, are specific frequencies at which, if you send an input that is a sinus and a harmonic signal at that specific frequency, it gets absorbed. The output of the system is zero. That's why it's called the zero. And in the opposite, for poles, what happens is that you have like the resonance phenomena. So if you send a sinusoid at that specific frequency in a system that has a pole at that frequency, then the output will explode. Basically, it will tend to infinity. But we saw that there are input and output directions, but we didn't really get into it. We didn't really clearly explain what was going on. And we will get to that today. So one other thing I would like to mention is I gave in class the more high-level, let's say, meaning of the poles and zeros definitions. But in last Tuesday's class, you saw a more, let's say, structured method to actually calculate the poles and zeros, the minors method. So that is good. And check out the course notes if you missed that. So what are the next steps now? The next steps are finding developing measures of sizes of signals and systems, norms, then figuring out what exactly does directionality mean in a MIMO system. And once we have these tools developed, we can finally start looking, in the same way as we did for seesaw systems, at stability, performance, and robustness, which are the only reasons for which we develop controllers. So let's start with norms. So what are we going to look at today? So raise of hands, how many of you know what norms are? You all know what norms are, right? Great. So you know the difference between, how many of you know the difference between, I don't know, a vector norm and a matrix norm? There are even norms of matrices. I didn't know that either a long time. But anyways, so nobody knows that there are norms of matrices? Anybody has an idea on the difference between norms of vectors and norms of signals, for example? Different thing. A vector is a collection of numbers. A signal is something that varies in time or in frequency. So that's different norms. Okay, so we will look at norms, and we will distinguish them in two big, I mean, it's not that we distinguish them, but we'll notice that they have two different properties. The vector and the matrix norms, what they do is that we can consider them as if they measure over space. And when we say space, we mean the different components of the vector or of the matrix. That means over the different channels of the MIMO system, okay? But that's not good if we want to get where our objective here is evaluating what is the relationship between the input and the output of a dynamical system, because we're studying MIMO systems, which are dynamical systems. So just looking at static channel-wise measures, that's part of the story, but not all of it. We have to head towards something that includes the dynamics. So we will first start by looking at the static norms, then we will extend, we will look at what it means to look at time or frequency norms of signals, and eventually we'll end up formalizing the concept of a system norm, which is well, we'll get to it. So what is a norm? A norm is an operator that is defined on some space. We will not get too picky here with the math today. You have dedicated courses where you can look at, we could speak half an hour only what are the nature of spaces, such that norms get defined in a different way, but it's beyond the scope of control systems. So it is important that a norm has 4 fundamental properties. So think of a norm as a length, okay? Like the length of something. If you want to measure a length, well, and we have to define the properties of whatever operator we use to define length, we want the length to be positive because there's no such thing as negative lengths. That's property number 1. Property number 2 is, well, if the length is 0, it means if the norm of something is 0, well, I hope that that's because the actual thing we're measuring is 0. There should be no other solution, no other shape of a signal, a norm, a vector, a signal, a vector, a matrix, or whatever it is, that provides a measure that is 0 apart from the signal being 0 itself. That's property number 2. Then we would like the norms to be such that if we take something and we evaluate the norm, we get a length. If we multiply that something by a scalar number, we just multiply it. Well, then the multiplication constant will just get out of the norm and multiply the original length. That's property number 3. And that works for any constant, positive or negative. And finally, the fourth property is that of the triangular inequality that states that the norm of a sum of two objects is smaller or equal than the individual sum of the norms. It's called triangle inequality because it's easy to recall if you just remember a triangle. And typically, one of the sum of two of the sides is smaller than the sum of the two things independently. So now, these are general properties of the norms, but depending on how we choose the objects x and y, we can define norms of different things, and that's the whole story we'll be telling today. So first, we look at vector norms. Let me just say something. There are many norms, many norms. A norm is anything that satisfies those properties. You can sit down and define your own norms, okay? We will just focus on a few norms that are the ones that have, let's say, engineering applications, meaningful meanings that are important for where we're heading. That is in the development of controllers. So the general definition. Let's take a vector. Imagine a vector as a vector is just a collection of numbers. It's static. There's nothing going on. Imagine it as if we're taking the input, for example, of multi-input, multi-output systems that in theory varies in time, but we're evaluating it only at a specific time instant. So it collapses into being a static vector. We can define, generally speaking, the pth norm, pth order norm, the pth norm of a signal as the pth root of the sum of the pth power of the absolute values of the components. It's easier defined than said. P can be any natural number, and we focus only on two norms, which are, sorry for no pun intended, the 2 norm and the infinity norm. So the 2 norm is arguably the most famous. It's the Euclidean norm. It's the one you've studied when you were in elementary schools. You draw a vector on a Cartesian plane, and it's the actual modulus, the length of the vector, okay? Are there questions? The 2 norm of a vector is the shortest distance between 2 points, okay? Very easy. The infinity norm of a vector is defined as the maximum component, the biggest component of the vector. So it's the component that has, of course, in magnitude, the biggest value. These are static, simplest things you've seen many times before. Now we step it forward to a second, and we look at static matrices, okay? So what we're doing is we look at static vectors, static matrices, then we look what happens as a static vector passes through a static matrix, and then we look dynamic vectors, dynamic matrices, put everything together, we get the system norms. So matrix norms are on top of satisfying the 4 properties that we saw before, the homogeneity, the triangular inequality, and so on. They satisfy this multiplicative or actually sub-multiplicative property, which means that if you take the norm of a product of 2 matrices, that's smaller and equal than the product of the 2 norms. Okay? This is a very important property, as we will see later today, because it allows us to study the series of systems. So suppose we have a matrix of some arbitrary dimension. It doesn't have to be square. We can define again, think about a static matrix as a transfer function of a MIMO system evaluated at a specific frequency, okay? So sometimes we get maybe confused when we say, we've got this transfer function, it's g of s, okay? And then we say, no, it's g of j omega. So let's think about it this way. If you write it as g of j omega, and you consider it at a specific omega, you say at frequency 2 radians per second, then that's a static element. It's a static object. It's just a static mapping between input and output. If you instead write it as g of s can be any frequency, we can consider that as a dynamic system, okay? So it varies. Here we're considering, you can imagine this static g as if it were a transfer function evaluated at a specific frequency. So in the same way as we did for vectors, we can consider the 2 norm, which in this case it's called the Frobenius norm or the Euclidean norm, which is just the square root of the sum of all the elements of the absolute values of all the elements of the matrix squared. Fundamentally the same thing as before, but generalized to a matrix. And it can be shown that this can be expressed as the trace, that is the sum of the diagonal elements of the product of G transpose G, that asterisk is the conjugate transpose in the sense that the elements of G can very well be complex numbers. They don't have to be real numbers. So in the case that they're complex numbers, the Hermitian transpose or the conjugate transpose, what it does is just takes the conjugate, so the minus in front of the imaginary parts of the components that are complex, and you then take the transpose. So when you multiply G transpose conjugate with G, you get a square matrix. You can sum up the elements on the diagonal. And we will see that this G asterisk G is actually an important element, an important actor and for Fermi systems. It will be at the basics of the singular value decomposition, which is the way to look at the favorite directions of a MIMO system. Then we define the maximum element norm, which is, as before, an analogy to the infinity norm for a vector. It is something that just finds what's the biggest element of a matrix. And it's worth noticing, there's a typo here, the second one is not the Euclidean norm, that this does not satisfy the multiplicative property, but I added it here just for completion so that you can do the comparison with the previous norms. So these were two static things. On their own, we don't really mind, we don't really care too much about them. But what happens now if a static vector passes through a static norm? So there's this concept of induced matrix norms. An induced norm, it's called induced because it's caused by a vector that passes through a matrix. So we can imagine, of course, our typical system where we are sending in an input and we are looking at the output. And we can define the gain of a system as the ratio between a norm, a vector norm of the output with respect to the vector norm of the input. Now we know what vector norms are, so we're good. So generally speaking, we define the induced P norm of a matrix as the ratio between the output and the input. Here, the second equation is just to say, now forget about the max for a second. The ratio between the norm of GW and W, it's nothing but the output over the input. The norms of the output over the norm of the input. And what we're looking at here is, what we're measuring here is what is the maximum possible gain in any direction. So if we just constrain the input vector to have a constant length, constant length doesn't mean that we're specifying which direction this constant length is. Imagine a unit vector in the Cartesian plane. It can always have unit distance from the unit length, but it can be oriented in any possible direction in 360 degrees, right? So when we're writing that second equation, what we're saying is as long as we're sending in an input that is not different from 0, we evaluate the ratio between the length of the output, the size of the output, and the size of the input, and we call that the induced matrix norm. Depending on which norm you choose in the ratio, it's defined in different ways. So the pth norm, you can have p equals 1 or 2 or 3, infinity, you can put whatever you want. So before getting there, it's important to notice that the third term of the equality, which is fundamentally the same thing as the second one, and it just says that if we take a unit vector and we spin it around, we look at all the possible directions, well, we get the same result. So if we particularize the p norm to a 2 norm, so we plug p equals 2, we get the induced 2 norm. And it's relevant, as we will see later on, because it turns out that it can be expressed as the biggest singular value of the matrix. We will see singular values just in a while, but suppose we... So it's the biggest eigenvalue, we know what eigenvalues are, of the G Hermitian transpose times G product. And then we look at the induced infinity norm, which is, as before, the biggest absolute value of the elements of the ratio between the input and the output. So why are these induced matrix norms relevant? Because they are, all induced matrix norms are matrix norms. Sounds like just a way of saying, but what it means is that they satisfy, on top of the 4 properties of norms, they satisfy that nice submultiplicative property. So why is this good? It's good because we saw that through induced norms, we can evaluate what's the gain, the maximum possible gain of a system at a specific frequency. Okay? Now, what if we have a series of systems, one after the other? Happens all the time in control systems. On the direct branch, you have the controller, then you have the plant. No, so you're not just going through one system. Well, the induced norms satisfy this submultiplicative property, which means that if you evaluate the series, we can express the ratio of the norms, of the output to the input of the origin, of the beginning of the branch, as simply as the product of the induced norms. So it makes it very easy peasy to evaluate, to get a bound on what is the maximum possible amplification of a signal if you pass it, of a signal at a specific frequency, if you pass it through a system. Any questions? I see some confused faces. Speak up. No? Okay. So now let's add a dynamic component.
Jacopo, there is a question here in the back. It's difficult.
Let's pass it a little bit at a time. Can you just throw it up, 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 go, go, go? Here we go.
Can you recap on the bottom part of the page, of the last page?
Sorry?
What it meant? Can you recap that?
This one?
No, on the last page. Yeah.
This one? This one?
Yeah, there.
Okay, so the idea is that, so we define induced matrix norms, right? So induced matrix norms are answer the question, what happens if I take a static vector and pass it through a matrix, okay? It's called induced because it's the vector that's causing this norm. In particular, it measures what's the gain that a system can bring in any possible direction, okay? Of any possible input direction. Now, we said that induced matrix norms are all matrix norms. So on top of the 4 regular norm properties that we saw at the very beginning, they satisfy this extra property that if you do the norm of the product, it's less or equal than the product of the norms. Why is this relevant? Because suppose you have only V, G1, and W. Okay, so first the system. By definition of what we said in the slide before, we can evaluate the ratio of the norms, the maximum gain of the system G1. But then what we really care about when we'll go and look at control systems is we care about the actual input-output relationship. So the intermediate signal is relevant, but up to some point. So what's the relationship between the interconnection? How does this gain change if I hook up a bunch of different blocks in a row? And thanks to this property, we can see that the interconnection is evaluated as simply as just multiplying the different gains, and that's it. So signal norms instead are, we're always talking about the same concepts, but we are increasing the complexity of the object that we are using to evaluate the norm as we go. Signal norms are basically the same thing as before. A pth norm is, instead of just the pth root of the pth power of the magnitude of the sum of the magnitudes of the components of a vector. Now it's the same thing, but it's integrated over time, for example, or frequency if we define it for a signal and frequency. So there's the integral part as well. So what we're doing here is we're not just averaging over channels, but we're averaging over time as well, okay? So it's not a spatial norm only, but it's a temporal norm as well, or temporal could be even frequency norm. So the pth norm is the general expression, and we can, as usual, look at the 2 norm, which is the 2 norm of a time signal is arguably the most famous norm there is, because it measures the energy of a signal, whatever that means, okay? And so often it happens that one wants to, for example, minimize the effort you put in controlling a system, right? That makes sense. Suppose you're sending a satellite to the moon. You might want to minimize the amount of fuel you need to get there, because adding a lot of fuel to a rocket means spending a lot more money, because the rocket has to be big, the tanks have to be big, or the rocket has to be bigger. So minimizing the input, the cost, energy, in order to achieve an objective could be something that makes sense. In the same way as you might want to minimize the effect of noise on a system, you might evaluate what's the energy associated with this disturbance. So it's a relevant norm. Another norm that is relevant in a different way, but still relevant enough to mention it among the many different norms there are, is the, again, infinity norm, which evaluates what is the... So do you guys know what a sup is? A supremum? Raise of hands. It's an ugly one. I don't like it either. So it's basically the least upper bound. Okay, say you have... so it's basically, you can think it as a maximum. It's the maximum value, okay? But since we have to be precise, there are some signals. Imagine like the output of a first-order system. That it's... actually, I have a graph of this just in a few slides. But the idea is, imagine that if the maximum value of a signal is achieved only at infinite time. So technically speaking, it's not really the maximum, because the maximum is defined in finite time. So the supremum is, what's the smallest possible thing I can take, such that it's the maximum of the signal over infinite time, over all times. So it's the least upper bound. And in fact, here it is. Let's look at 2 simple systems, okay? The blue one and the red one. So the blue one has... the least upper bound, that is, we have to look at some value that is above every possible value of the signal in all times. We see that there is no infinity norm of the blue signal, or at least there is, and it's equal to infinity because it has an asymptote. So there's no way we can bound it. While the red signal, the orange signal, whatever it is, if we were to define it just with a maximum, it wouldn't work, because that's asymptotically tending to something. So there's always a greater value. But we can find a bound, something that just is bigger over all possible times, and it's the infinity norm, which is whatever that value is. Okay? If we instead look at the 2 norm, we can see that the 2 norm of the blue signal will have some value, some finite value, while the red signal continues growing over time forever, right? So the 2 norm, which is the energy of a signal, it's the sum of each component squared over time. It will go to infinity, because it's always growing. There's always more energy that's added to it. So this is to say that while we were looking at static norms, the difference between choosing between different norms wasn't necessarily so striking. When you talk about signals, they can have radically different results. So it's important to understand what we're calculating. So now we can put everything together and think about it as norms of a dynamic system. So now we're not just evaluating all of this at a specific frequency, but we're evaluating this over all possible frequencies. And it's just a little step forward with respect to what we said before. We always define a 2 norm, we always define an infinity norm, and their concepts are always that of energy and of maximum value, but this time over frequency. And we average over all possible values of the frequencies. So the 2 norm can be imagined as something that now takes so the 2 norm of a dynamic system is something that measures on average the gain of a system over all possible channels, but even over all possible frequencies. So it's averaging out channels and frequencies. While the infinity norm is picking over all possible frequencies what is the maximum gain. So if you think about for example, I don't know, sensitivity function, okay? Even for a CISO system, it doesn't really matter at this point. Having a big value in the frequency response, in the magnitude of the frequency response of a sensitivity function, what does it mean? It means you're amplifying a lot, some disturbances or noises that come in, okay? That's bad. In fact, we looked at loop shaping, which is a way to say, hey, basically, we said at some point, I think it was lecture number 2, that we could imagine all control systems as a way to make the sensitivity function small, appropriately small in some ranges of frequency ranges where we care about. So having a high peak of a magnitude of a sensitivity function is bad because it amplifies unwanted inputs to the system. So the infinity norm of a system, to wrap it up, measures a worst case scenario, okay? What's the worst case scenario? It's the maximum possible gain you can get over all possible frequencies, over all possible directions in a dynamic MIMO system. It is very famous because it's useful, and it's useful because, A, again, it satisfies that submultiplicative property, which is good because it allows us to evaluate the interconnections of systems. And second, because it again represents this worst case scenario. So we're going to move forward towards looking at robustness in systems. And robustness means how does your system fare when you don't really know something about this. You have uncertainty in the, for example, model parameters of the model of the system. So we will see that when you have uncertainty, it means that all you can say is, look, if I send this input, the output might be in this range. I'm uncertain because it depends on what the system actually is. That's the whole point of model uncertainty. Thanks to this norm, we can always evaluate the worst case scenario. So when you want to design a controller that is robust, well, it might make sense to guarantee that the worst case scenario is good enough for us. Might be a conservative design, but definitely it's important. So in summary, what we did is we looked at this crescendo of norms. And vector and matrix norms, imagine them as a time signal or transfer functions evaluated at a specific time instant, at a specific frequency in case of transfer functions. And then we looked at dynamic norms, signal norms and system norms, which take in consideration the frequency or the time component as well. And we saw that what we really care about is these system norms that evaluate the gains of a system over all frequency and over all possible channels, depending on how we define it. Are there any questions? Slight amaze. Are there any questions? Yes, no, maybe? Comments, doubts? Good enough for me. We have 5 minutes to go, so maybe we can start, and we will continue later this part. So now, we have, what did we get to? We defined the tools to measure stuff. Good, because now that we have a way to measure signals and interactions of signals and systems, we can now finally start taking into consideration what do we want small and what do we want big, because we have the ability to actually define big and small. The second important property that we wanted to look at of MIMO systems was this concept of directionality. And the way we're going to look at it is by leveraging this result of linear algebra that is called singular value decomposition. So is it something new? Is it something you've never heard about? Even if we are framing it in MIMO system, these weird things, but the concept of directionality of favorite directions of a system, of a matrix, it shouldn't be new to us, because the eigenvalue problem is has very similar relationships to this, has very close relationship to this. You might recognize that equation on the top is the definition of the eigenvalue problem. That is, let's take a matrix A. If I send in an input in some direction, and I get an output that is in that exact same direction of the input, but just multiplied by a gain, we call that vector the eigenvector, we call that gain the eigenvalue, okay? And if you do this for all the possible eigenvectors and values of a matrix, you can even define some transformation functions that make your matrix diagonal, okay? What does that mean? How cool is that? It means that somehow those eigenvectors are basically the favorite directions of a matrix. you will see that this is like arguably one of the 5 most important concepts in engineering. You'll see it has huge applications even in the design of mechanical and dynamic systems, in the sense of, I don't know, if you want to evaluate, always thinking about satellites, if you want to evaluate what's the equations of motion of a satellite as it turns around, well, the first thing you do is you find the favorite directions, the eigenvalues, the eigenvectors of the inertia matrix of the satellite, so that you can make all your calculations much easier. So diagonalizing, finding the favorite directions of a system is something that you already know. So what's the difference between a singular biodecomposition and an eigenvalue problem? It's that the eigenvalue problem basically is a particular case in the sense that it assumes that the input and output directions are the same. Okay? Well, generally speaking, that's not true. So we will look at the singular value decomposition, and we will see that it produces two outcomes, which are the singular values, that is, the gains over the favorite directions of a matrix, and the left and right principal directions, which are the equivalent somehow in concept of the eigenvectors, but of input and output, as we've seen that there is this distinction to be made for MIMO systems. So before we get into this, I think it's good to take a pause. We can continue after the break. Okay, hello? Here we go. Yes, sir. You need the cube of terror. It's up there. So could you please throw this thing down, and then it has to go there. I told the folks that it wasn't a good idea to throw this thing around, but hey. So, yes, sir.
I have a question for,
yes.
About the for example, the pole cancellation, not pole cancellation, about the output. If you have the frequency of, for example, pole or 0, and you give that as an input to your system, then why should the output, for example, be 0 if we have a transfer function 1 plus s? And we give an input of omega equal 1. Mm-hmm. Then we just have a transfer function 1 plus I, because we have a complex input. Why should the output now be 0?
If it's a 0 of the system, and we're talking about a MIMO system, and we're sending that input that you said at a specific frequency, which is the frequency of the 0, but even at a specific direction, then we will get 0 as the output of the system. And we will see this in a few slides. There is an example at the end of the singular value decomposition that breaks down the problem into input and output directions, and we will see basically exactly this for zeros and poles.
But I mean, also applied to single input, single output systems, why should the output be zero? Because, for example, in this example where I have a transfer function 1 plus s or 1 minus s, if I put in the complex instrument...
1 plus s is not a rational transfer function.
Okay, let's say 1 over 1 minus s.
1 over 1 minus s, okay.
And I have an input of omega equal 1, equals to 1.
So yeah, at steady state, if you look at the steady state response, you get as an output a signal that has, it's always a sinusoid, then it has same frequency, actually shifted by the phase of the system, and amplitude that is multiplied by the gain of the system. And the gain is the modulus of the transfer function evaluated at that frequency. So 1 over 1 minus 1 is 1 over 0, which is undefined. But as we get close to that frequency, the magnitude goes to infinity. So that would be a pole, right?
Yeah. So we would have a pole at 1 in this system. But if we look at the amplitude of the transfer function, it doesn't go to infinity, because the amplitude of the transfer function would just be the amplitude of 1 over the magnitude of 1 over 1 plus 1.
Maybe we can look at this offline at the end of the class, so we can actually write it down.
Yeah.
Okay, so we left off with the singular value decomposition, and we said that it's good because it allows us to study the directions of a multi-input, multi-output system. Okay, So what is a singular value decomposition? Let's start. The story starts from picking a matrix that, beware, it's not necessarily a square matrix. This applies to any matrix. And let's suppose it has L by M dimensions. And again, it's useful to imagine it in order to link the mathematical stuff we're talking about to the actual control systems related application. It's good to imagine the transfer function the matrix that we are evaluating the singular value decomposition of as a transfer function evaluated at a certain frequency. So the singular value decomposition says that you can always express a matrix as the product of three matrices. U times sigma times V transpose, conjugate transpose. And we define the U matrix is a collection of vectors that have dimension L by L. Let's write this down. Just a very small note. It's something we said last time as well. The idea is how to figure out the dimensions of matrices. Now, so say we are evaluating, what did we call it? G. We are evaluating the singular value decomposition of a matrix G that is a matrix that has complex entries and what was it, L by M? And it has L by M dimension, okay? And we say, well, G can always be expressed as the product of three matrices. Something we call U, something we call sigma, something we call V. And we ask ourselves, what are the dimensions of these matrices? So we said G is an L by M, right? This is L by M. So in virtue of what we said last week, the leftmost dimension of this has to be L. The rightmost dimension of this has to be M. And the intermediate dimensions must match. This is always of the dimension of the original matrix. Therefore, this is L by L, and this is M by M, because these two have to match. Otherwise, you can't do the multiplication. So we define the U and V matrices as collection of vectors. And these are unitary matrices. And we will see exactly what that means in the next slide. But the idea is that every vector has unit norm. And the whole matrix, if multiplied by its transpose, gives an identity. So the vectors U1, U2, UM, and V1, V2, Vm are orthonormal with respect to each other. They're orthogonal and have unit length. And then we have the intermediate matrix, the sigma matrix, which is a diagonal matrix that has the main block of the diagonal is diagonal as well, and has a collection of numbers, of scalars, that we call singular values. And we will see what they actually represent. Singular values are always labeled in such a way that the sigma 1 is the biggest one, up to the sigma L or M, depending if what are the dimensions of the matrix. If it's L, it's bigger than M, or M is bigger than L. They have decreasing magnitude. So the sigma 1 is the biggest one, up to the last sigma K, that is the smallest one. And we can evaluate the singular values as anticipated while talking about norms before, as the square root of the eigenvalues of this magic matrix that is the product of G conjugate transpose and G. So what does it mean? First of all, this is very unfortunate. I hope some of you are very fairly care about notations, and it's important to have consistent notations. Unfortunately, I don't get to choose the notations for singular value decomposition because you'll find it in literature like this all over the place. And it's very unfortunate that the output directions are defined as a big U, which is what we typically use for inputs in control systems, so please don't get confused. But we call the input principal directions of a matrix as the V matrix, the one on the rightmost side. And it's made of vectors, as I said before, V1 to Vm, that are m by 1 vectors, such that the product, the inner product of two vectors, is always equal to either 1 or 0. It's equal to 1 if they are the same. If you multiply a vector by itself and you evaluate the 2 norm of it, I didn't explicitly say it, but it's written in the slides of the second slide, the vector norm thing. You can express the 2 norm of a vector as a simply V transpose V. So they're equal to 1 if they are multiplied by themselves. Their 2 norm is 1. And they're orthogonal to each other. That means if you project one of these vectors on any other, you get 0. And we use this notation, the delta of Kronecker. You all know what a Kronecker delta is? Raise your hand if you know what a Kronecker delta is. Fantastic. Okay. So then the output directions have the same property. They have their orthonormal base, and they have and the matrices U and V are unitary matrices. What does it mean? It means if you multiply V conjugate transpose V, you get an identity matrix of dimension M and an identity matrix of dimension L if you do the same trick on the output directions. So if we look at the definition, G is equal to U sigma V, and we leverage the unitary property of the input directions, we multiply both sides of the equality by V, and you get this passage here. We just multiplied by V here, and right multiplied V here and V there. V transpose times V is equal to the identity, and we get GV is equal to U sigma. So there, if we now just evaluate the columns, so one column at a time, you can clearly see why they're called input and outputs, because the idea is you send an input VI that passes to the system G, so V are the inputs, and it produces as a result, along a direction U, a scaling factor, again, times in the direction U. So the U's are the output directions. And from here, we can see, consider that the sigmas are scalars, they're just numbers. We can take the norm on both sides, any norm, evaluate, use the properties of norms, so the sigma goes out of the norm here because it's just a scalar, and therefore we can see that the singular values represent the ratio of the output norm to the input norm, which is the induced matrix norm, right? So what does this mean? Suppose you have a singular value decomposition and you find your input and output directions. And we said that the singular values are ordered in such a way that sigma 1 is always the biggest, and sigma k, which k is the minimum value between L and M, is the smallest. So we call the strong direction the one associated to the biggest singular value. It's the direction, an input and output, that has the biggest gain associated with it. If we were to send a unit input in direction V1, what we would get is an output that is tilted and magnified to the maximum possible gain of the system, which is, so this is a notation. When you use the top bar on singular values, it means it's the biggest one. If you use the underscore, how do you call it? You underline the sigma, it's the smallest one. And they can be graphically represented as the biggest and smallest semi-axis of the ellipse of the directions of the outputs. And this, of course, is a drawing that holds for a two-dimensional system. So, but the idea is if we send in an input that is aligned with the strong direction, the one associated with the biggest singular value, you get the biggest possible amplification of the output. And the smallest one if you do it for the weak direction, which is the one corresponding to the smallest singular value. So it's nice that we have this property, because now we know that regardless of the direction in which we're sending the inputs, the output will always be bounded by the maximum and the minimum singular value, because the ratio of the norm of the output and the norm of the input is defined as the singular value itself. And thanks to this singular value decomposition, we order things in such a way that we can bound this maximum gain of a system between the singular values. So singular values are really important because they tell us this is where you'll end up for sure. Bigger than the smallest one, smaller than the biggest one. There's this entity that is defined. It's called the condition number of a matrix. That is a very coarse measure of the directionality of a MIMO system. And it's the ratio of the maximum singular value to the smallest singular value. By definition, of course, it's always bigger than 1 because we ordered them in such a way that the biggest one is bigger than the smallest one. And why is it relevant? Mainly because having a very high condition number typically means that your system is very hard to control. Why? Because I think it's intuitive to think that a system is easy to control when your inputs have a big effect on your outputs, right? So if I can send in an input that changes an output significantly, that is with a big gain, then it means I have the potential to change that output in the way I wish. Of course, this is very generally speaking, but the idea is a big gain associated to a certain output allows us to change it a lot, while a small gain associated to a certain output means we can do pretty much whatever we want with our inputs. But if then you multiply it by a very small number, it means the effect you can have on the output is very small. So having a big condition number, if it's big because the denominator is very small, then it means the system is very difficult to control. If it's big because the numerator is very big, then it's not necessarily a bad thing. It can actually be a good one. I think you can imagine this with a nice physical example that is in your book. Imagine you're at the supermarket and you're moving a cart, okay? So a cart has wheels. So suppose you want to move it, there are 3 directions in which you can send your input, and 3 output directions. The outputs, the directions are either straight, like you push it, or laterally, or you pull it up, okay? So the idea is that the direction that has the biggest singular value associated, the one that if you give a unit effort in pushing, a unit effort in input is clearly the pushing direction, because if you just touch your cart, it moves forward a lot. There's a big gain between the input and the output. Say instead you are in the middle of a lane, you're choosing something, and somebody passes by and you're bothering them, you have to move your cart sideways. Okay, moving a cart sideways requires more input, more effort and input to move it sideways in a significant amount, of a significant amount. Therefore, it has a gain associated with that direction that is smaller. Of course, the minimum singular value of this cart problem is, imagine you have to lift up your cart. Okay, you have to literally pull it up in the z direction. That means that you need to that direction has a very small gain because you need a lot of effort in order to lift your cart very little. Okay, it's just to get an idea of the physical meaning of singular values. So the condition number, as we said, measures this conditioning of a matrix, and a matrix is said to be ill-conditioned if it has this value that is very big. Just a quick note, singular values, when you are evaluating them of a transfer function of a dynamical system, that is, we put the s in there, then it is a function of frequency as well. The definition we gave of singular value was for a static matrix G that we imagined as defined as j omega. But generally speaking, singular values are a measure vary over frequency. So in fact, if you recall the definition that we said before, the infinity norm, the worst case scenario of a system norm is the worst case over all frequencies. There is the least upper bound that it evaluates this over all possible frequencies. So, and of course, it depends even on the direction. Now we just saw that that graph means if you send in an input that is a unit input in some directions, then you get the output that is distorted and amplified depending on the directions of the singular value decomposition. And this is a simple numerical example that shows this very clearly. Suppose you have a second-order system and has 2 inputs, and you just evaluate the direction as the ratio of the 2 components of the input. Then you can see as just varying the direction, you get this wild variation of the singular values. So you call the lowest singular value just the minimal gain, the gain defined again as the ratio of the norms, the 2 norms of the input and output. And the maximum singular value is the worst case scenario, the maximum gain. So, okay, I hope, are there any questions on singular values, on their meaning? This is quite an important concept moving forward, so if you have doubts, express them now, or be silent forever. How is it that they say? So, okay, now how do we compute these singular values? Because it's good to know what they mean, but at the end of the day, we have to calculate them, right? So I put together a recipe, cooking recipe for singular values, and it goes as follows. First, you evaluate the eigenvalues of your G transpose G matrix, okay? Why? Because we saw that the singular values are defined as the root of these eigenvalues. Then we will find the input directions, which are the ones. Now, then you find your eigenvalues and you label them in such a way that the number 1 is the biggest one, and then in decreasing order. Then you build the sigma matrix in such a way that it has the same dimensions of your original matrix, as we saw by looking at the dimensionalities. And you place the singular values. We'll do some exercises of this, but it's good to go through it. Then it's up to defining what the right singular vectors are, that is the input directions. And you do that by finding the eigenvectors of the G transpose G matrix. And once you have those, you can find the input directions by leveraging the definition of singular values. There are some corner cases that make it not as straightforward as it looks. And let's look at a few. So suppose that we want to do the singular value decomposition of a matrix that is G equal to, it's a square matrix. We'll start easy. What's it equal to? -2, 0, 0, 1. Okay? So it would be nice to see the rest. Step 1. We evaluate the eigenvalues of G Hermitian transpose G. In this case, this is just equal to G transpose because we have all real valued entries of the G matrix. Okay? So let's look at how this looks. So G transpose G is equal to what? It's equal to the transpose of this. That is the same thing because it's the diagonal matrix times -2, 0, 0, 1. And this gives us what? Row times columns, 4. Row times columns, 0, 0, 0, 1. Right? Okay, so step number 2. Step number 2 is what? From the recipe? Somebody read it out? Participate actively. So, what is step number 2? Find the eigenvalues. Thank you. How do we find the eigenvalues? So let's recall briefly what is an eigenvalue. Say you've got a matrix G. The eigenvalue problem is finding the lambda i's such that G minus lambda I is equal to 0. So how do we find the eigenvalues of this matrix? We just do G transpose G minus lambda I, and we set that to 0, so it's and we do the determinant of this. actually, we don't need to do this because this is a diagonal matrix, so it's trivial. So let me erase this. So this is a diagonal matrix, so it's obvious that the eigenvalues are 1 is 4, and lambda 2 is 1. Now, step 3. We can evaluate the singular values. Why? Because the singular values, the ith singular value, is defined as the positive square root of the ith eigenvalue of G transpose G, which we just computed. This means that our first singular value is the one associated to the biggest one. It's 2. The second one is 1. Okay, and step number 4. What do we need to do? We need to build the sigma matrix, the matrix of the singular values. So sigma, how do we go about doing that? Well, first of all, we use this. We go back here. This is an M. And we see that fundamentally the sigma matrix has the same dimension of the original matrix that you are trying to do this game of. So it's a 2 by 2. So this is a 2 by 2 as well. And how do we fill it up? We know it's a diagonal matrix, so zeros on the off diagonal. And here we put the singular values in decreasing order. So 2 and 1. Okay? Yes. No, so this is the root of the eigenvalues of the matrix. So the eigenvalue is a number. Yeah, there are no roots of matrix involved, even if I think there is a way to do that as well, but it's not what we're talking about. So what are we doing here? We found the singular value of the decomposition. So what's the next step in the recipe? Speak up. What's the next step? Any doubts? Which eigenvectors? Because it's not eigenvectors, actually. It's right or left. Say it again. Okay. So step number 5 is we want to go and evaluate. We're heading towards evaluating this matrix here. Okay, it's the input vectors. Why input? Because remember that G times V equals U times sigma. How do you do that? We do that by calculating the eigenvectors of the G transpose G matrix. So eigenvectors is, the definition is down there, but be careful. No, yes. Can you take the cube? You're hacking the cube? I think you need to use it because otherwise the people in the other room won't hear you. It's on, but it doesn't say anything. So Andy, can you take a look at it? Thank you. No? Okay, what can I say? Shout. Loud. Of course. That's because the meaning we associated with the singular value is that of a gain. So it's a positive. It's the magnitude, yes. Okay, so what was the next step? Is finding the V matrix, right? So the V matrix is a collection. What's the dimension of this V matrix? It's m by m, right? So m is 2. It's again a 2 by 2. Of course, here we have a square matrix, so everything is easy. But we will have to find 2 vectors, v1 and v2. Each vector is such that it's, of course, a 2 by 1. So we stack them together, and we get a 2 by 2. So how do we find the v1? v1 is going to be the eigenvector associated with the first singular value. Okay? So the way we do it is we solve the eigenvalue problem of G star G minus lambda I times V1, and this is V lambda 1, equal to 0. So make sure that here you don't plug in the singular value, you plug in the eigenvalue. Okay, we're doing the eigenvector associated to that first eigenvalue. So how does this look like? Lambda 1 is 4, correct? Here. So this part here becomes G transpose G is where? It's here. So it's 4, 0, 0, 1, and we remove a 4 from the main diagonal. So it's 0, 1, 0, 0, minus 3, correct? Okay, so now we need to find the vector. This is this part here. Now V1, it's a sum vector of two components such that the result is 0, 0, okay? So let's look at this product. What does it give us? It gives us two conditions. That 0a plus 0b is equal to 0, and 0a minus 3b is equal to 0. This means that b has to be equal to 0, because otherwise this constraint is not respected. And here we can pretty much have any values we want for a, because it's always multiplied by a 0, so it doesn't really matter. So it means that we can have the eigenvector is a vector like this, and we can choose it. We have to choose it in such a way that it has unit magnitude, right? So let's choose it to be v1 equals 1, 0. Now, this was to find v1. Now let's do it for v2. And for v2, it's pretty much the same thing. And what we get is 0, 1. I'll spare you the calculations. So the V matrix is now the collection of v1 and v2, as we wrote somewhere here. This is 1, 0, 0, 1. And we can note that it's a unit matrix, because if we do V transpose B, we get the unity, of course, because they're all identity matrix. This is a trivial case. Okay? Now, this was the step number 4. So we go to now step number 5. Now we need to find the last missing bit, which is the output directions. This is a collection of two vectors, u1 and u2. And instead of doing the same game we did before, what we will do is just leverage the definition that we gave of a component, column-wise, of the singular value decomposition. That was that sigma I is equal to let's step back a second. So let's look. We know that G is equal to U sigma V transpose. Therefore, GV is equal to U sigma. We do this by columns, so therefore GVI is equal to sigma I UI. Sigma is a scalar, so I can bring it over. Therefore, UI is equal to what? Is equal to 1 over sigma I times GVI. So all we have to do is now just apply this. So let's do it. So let's remember that sigma 1 was equal to how much? 2. And sigma 2 was equal to 1. So let's start with the first one. We get that U1 is equal to what? Is equal to 1 half G times V1. G was what? G was minus 2, 0, 0, 1. And the V1 was 1 and 0, correct? So this, we do the calculations, and it's 1 half times what? Times minus 2 and the 0. So this is minus 1, 0. Done. This is U1. Now let's look at U2. It's 1 over 1, of course. It's trivial, but just to explicit every passage. Minus 2, 0, 0, 1 times 0, 1 this time, which is V2. And this is equal to what? It's equal to 0, 1. Okay? So now we have our U. Now we can express, we finished, because we can verify that this U is actually a unit matrix because the components have unit distance and they're orthogonal to each other. And we can spell out now the singular value decomposition of G as what? As U1, U2. So minus 1, 0, 0, 1 times the matrix of singular values, 2, 0, 0, 1. And then the V output matrix transpose, which is V's were 1, 0, 0, 1 transpose, which is the same thing, but whatever. Okay, done singular value decomposition. What does this mean? It means that if you send an input in the direction associated with the biggest singular value, it's this one, you would get a biggest amplification and the smaller one in this other direction. Any questions? Yes, sir. I'm sorry, you need to use the ball.
Okay, it works again. In this case, the not the eigenvectors, the
singular vector, left or right singular vectors.
Yeah, the singular vectors, they seem to be, they seem to be like not orthogonal on each other, but they have like very different output direction. For example, if I look at the very left vector, it's minus 1, 0. Yes. And the second one from the right associated with it is 1, 0. Does this mean that my input and output will have, my input will have a very different effect in the system than the output?
Let's look at it from this equation. Or actually from this equation. So you're saying, I send as an input to the system a signal in direction minus 1, 0. What's the output? It's something in the direction of 1, 0 multiplied by this 2. So this basically means that if you send an input in that specific direction, what's going to happen? It's going to be amplified and then flipped over. Yeah. Basically. Does it answer your question?
Yes.
But then another thing, orthogonality of vectors implies that they have pretty much nothing to do with each other, because they have nothing in common. That's what orthogonal means, that if you project one on the other, you get 0. Like the x and y axis is the trivial example in the Cartesian plane. Okay, so now you might say, yeah, but this was easy because it was a 2x2 system. So let's try something a little bit less squared. I have to erase here, though. Okay, so back to us. So in the interest of time, do you prefer to see a non-square exercise or see some more theory? Choose. Raise of hands. Who wants to see another exercise? Another exercise. Okay. So let's now consider a non-square matrix. We will call this, what is it? 0, 2, 0, 0, 0, right? Okay, 0, 2, 0, 0, 0, 0. Are there any questions? Comments or doubts? No. Okay, step 1. Now we'll do it a little bit quicker. Let's find G transpose G. G transpose G is, how do we transpose this? We take the rows and they become columns. This is equal to, this is a 2 by 3, this is a 3 by 2. So the result is going to be a 2 by 2. And it's row times column 0, row times column 0. This is 0, this is 4. Okay, so step 2. Find the singular values of, the eigenvalues of that, right? These are diagonal matrix, straightforward. We label, so no, these are not singular values. Lambda 1 is equal to 0. Lambda 2 is equal to 4. Then, step number 3. I raised that too much. Really? Okay, so step number 3. We evaluate the singular values as the roots of the eigenvalues. So we label them such that the singular value 1 is the biggest one. So singular value 1 equals 2. Singular value 2 equals to 0. 4. We fill up the sigma matrix. The sigma matrix has dimension equal to where we're starting from. So it's 3 by 2. Okay? So how does this work out? We put on the diagonal in decreasing order 2, 0, and then everything else is 0. Okay? Then we have to evaluate the input directions, V, which are the eigenvalues associated with the G transpose G. So V1 is going to be G transpose G minus lambda is 4. So please note, here the eigenvalues, we just wrote them like this, how they happened, but then the singular values are ordered appropriately to avoid confusion. It's probably best if I just relabel this like this so it matches. Now we have to do minus 4i and find the vector v1 such that this is all 0. This is the eigenvalue problem. So how do we do that? We get G transpose G, which is somewhere here. And we subtract from the main diagonal 4. So what we get is minus 4, 0, 0, 0. And we find the components A and B such that this is equal to 0. And what turns out is that these two conditions have to apply at the same time. Minus 4a plus 0 times b is equal to 0. And the other one is 0 times a plus 0 times b is equal to 0. So here I'm writing these trivial things just to highlight that what we can choose to be whatever we want. So it means that v1 must have a equal to 0 to satisfy the first constraint. And the second one can be pretty much whatever you want because it's multiplied by 0. It's a free variable. We want v1 to have unit to norm, so we'll just plug a 1 here. Okay? And if we do the same thing with the other singular value, we will get v2 is equal to 1 and 0. Now, what do we need to do next? we need to find, so now we have the V matrix, which is going to be 0, 1, 1, 0. Now we have the sigma matrix, check. We have the V matrix, check. We have to find the output matrix, which is U. How do we find it? U1 is going to be equal 1 over sigma 1 of what? Of G times V1, correct? So sigma 1 we said is 2, so this is 1/2 times G. Where is G? G is up there. 0, 2, 0, 0, 0, 0 times V1, which is 0, 1. This is a 2 by 1. This is a 3 by 2. So yeah, we didn't do any mistake because we can actually multiply these two matrices. So we get 1/2 times what? Times this is going to be a 3 by 1 at the end. Please note that the U matrix is going to be a 3 by 3 if you just look at the dimensions we wrote at the beginning. So this is a 0. No. This is a 2. This is a 0. And this is a 0. OK? 1/2, 2, 0, 0. Nice. 1, 0, 0. It's unit norm. Check. And therefore, we can take it as good. Now, here comes a little bit of a tricky part. Because U2, now the singular value 2 is 0, so there's no way in the world we can write down what we wrote before because it makes no utter sense. So how do you find the U2 and the U3? Because U is a 3 by 3, and we need to find 2 more vectors. So there are 2 ways to go about this. So 2 ways. One way is so we have to basically fill up this matrix with the U matrix with 2 vectors that are unit norm and they're orthogonal to the other one. So we could find a vector W that has components A, B, and C. Please, these A's, B's have nothing to do with the other ones, so it's very best that I change them. Let's call them W1, W2, and W3, such that V transpose U1 is equal to 0. So it's orthogonal to the vector U1. Another way of doing it, and then you can choose which one you prefer, we can just compute the U vectors as the eigenvectors in the same way as we computed the V vectors, but not for G transpose G, but for G transpose. We flip over the... So otherwise, we can choose them as not G transpose G, but G transpose minus lambda I times ui equal to 0. We basically solved the eigenvector problem, but for the transpose of the original. It's not G, as I said before, not G transpose G, but the inverse. So in the interest of time, I'll go with this method, because in this particular case, it's just quicker. It's one computation instead of many more. So W transpose times U. What does it mean? It means W1, W2, and W3 times U, which is 1, 0, 0. This is equal to what? It's equal to W1 plus 0 times W2 plus 0 times W3. And this has to be equal to 0. They have to be orthogonal, OK? So what does this mean? This means that the only thing that is sure is that W1 has to be equal to 0 of the V vector. But then there are 2 variables that are free, because whatever you choose them to be, they are multiplied by 0, so they satisfy the orthogonality constraint. So we can just choose the U2 vector and U3 vector to be respectively 0, 1, 0. That is, we consider W2 equal to 1 and W3 equal to 0, and 0, 0, 1. Why? Because if we choose the vectors in this way, then the matrix U becomes a nice identity matrix that, again, is orthonormal, and that's a constraint of the singular value decomposition problem. So I understand that we are out of time. And therefore, I would like just to do a last note, that is, if you do the same exact thing, but now you consider the poles and zeros, take a transfer matrix G of S. evaluated at the 0, we said, what are the directions of input and output directions of a 0? Well, if you're evaluating a transfer function at a 0, it means that if you send an input in that direction, the output is 0. What does it mean? It means the gain of that principal direction is equal to 0. So if you do the singular value decomposition, what you will get is that one of the two singular values is equal to 0. So what's the input and output directions of that 0? You just pick the corresponding right and left singular values. One tricky thing is that, in theory, you can do the same thing with poles. But this is very wrong to write, okay? Never write something is equal to infinity because it doesn't make sense. But let's just imagine it for a second that it's equal to infinity. If we were to follow the same process, you would get infinity in all the entries and it wouldn't work. So what you do is you just add a very tiny little epsilon bigger than 0. And what you will get is a very huge eigenvalue and a singular value and a much smaller one. And the input and output directions of that pole are going to be the corresponding ones, and just plug in an epsilon that is very small. You can do it by hand numerically. You just put 10 minus 4, put 10 minus whatever it is, and you'll get a very good approximation of the input and output directions of a pole of a MIMO system. Sorry for keeping you 5 minutes more.